All right, let's look at an example second order circuit. This one's a little bit more complicated than just our basic series or parallel RLC, okay? What we're going to do, our goal here is to find V of t, which in this case is defined to be the capacitor voltage for t greater than or equal to 0. So that ultimately means we need to go through the 6-step process that we've talked about in class. All right, and specifically we're interested in going through those steps that we need to be able to figure out V of t. All right, so we're going to do that. Now, the thing that's important to remember, before I do any of these problems, I should really make definitions for all of my branch currents, like I sub c. In this case, I've called this guy I sub 2 through the 2 ohms. And this is just I. All right, it's been told to us that it's I. And I've also defined the voltage polarities across everything. Okay, so let's go through this. So in step 1, we find V sub c of 0 minus, I sub L of 0 minus. Okay, so those things we find here, these guys we find right before the switch moves, right? So right before switch moves. And these guys over here, we find right after, okay? So there's really kind of 2 sub-steps here. In reality, because I've asked you for the capacitor voltage, I really only need to find V sub c of 0 minus and I sub c of 0 plus, but we'll find them both, I guess, just for good measure. All right, so let's do that. Let's do step 1. And let's start with the before the switch moves stuff. So we'll do V sub c of 0 minus and I sub L of 0 minus, okay? So let's draw the circuit in that condition. Well, remember, our basic assumption here is going to be that the circuit has been in steady state for a long time. So if the circuit's been in steady state for a long time, I know that all my d by dt terms have gone to 0, which basically means that my L is a short and my C is an open. All right, so a long time after all transients have died out, I know that L is a short and C is an open. Okay, so right before t equal to 0, if that switch here has been open for a long time, then I have my 4 ohms. My L is a short. Now, because this switch is open, this branch with the 2 ohms doesn't matter. And I just have this. So the capacitor is an open. So I have that. V sub, well, and I'll call it V of 0 minus. Like that. Now, but that's the circuit, right? Because remember, the 2 ohm branch isn't there because the switch is open. The inductor is a short. The capacitor is an open. So it's pretty easy to see what's going on here because V sub c of 0 minus, the initial capacitor voltage, is clearly got to be whatever that source is. This source was 12 volts, right? There's no current flowing in this circuit. So there's no current flowing in this circuit. I see that V of 0 minus has to be 12 volts because there's no voltage drop in that resistor, right? I know there's no voltage drop in the resistor because the current at this time is clearly 0 amps, right? I have an open circuit here, so there's no current that can flow. All right, so I've determined the 2 conditions that I can from that circuit. The one that I'm going to need is this guy. All right, so I'm going to create up here some things that I know I'm going to need for myself. So I have V of 0 minus equal to V of 0 plus is equal to 12 volts. Okay, I'm going to need that later. So I'm going to create a little box up here of stuff I know that I'm going to need in my later steps. Okay. Now, the other part of step 1, so I guess I'll call this, I don't know, sort of step 1b, is to get I sub c of 0 plus and V sub L of 0 plus. Basically the stuff that I'm going to need right after the switch changes. So if I look at the circuit over here, so I'll keep the circuit in view here on the screen. Right after the switch moves, I have my 12 volt source. I have a resistor. Now in this case, I have to replace the inductor with a current source and the capacitor with a voltage source. Remember, our basic theory is that for a really short period of time, right? For a really short period of time, V of 0 minus equals V of 0 plus, and I of 0 minus equals I of 0 plus. All right, and that's true for the capacitor. This is true for the inductor. This means that L is a current source, and that means that the C is a voltage source, like that. It's only true for a really short period of time. All right, so we're going to do that here. We're going to say, here's I of 0 minus, that's the current source, or so that's the current source that represents the inductor. Here's the 2 ohm resistor, like that. And then my capacitor becomes the 12 volt source. Okay, so this is V of 0 minus. Okay, and I of 0 minus was 0 amps. Okay, so again, let's see what to do with this guy. So a current source that's 0 amps, I can think of that as just simply a open circuit. Okay, and the voltage across there I can solve for. Okay, and the current through here, which is the capacitor, I sub C of 0 plus, I can solve for. So let's try to do that here, right? And let's focus first on VL of 0 plus, because that's actually pretty easy to figure out. So by KVL, I'm going to do KVL around this loop here, right? I'd say, and I start here in this corner and I go around. So 0 equals negative 12 plus, okay, I don't do anything across that resistor because there's no current flowing. I have an open circuit thanks to the inductor. And then I have 12 volts here plus V sub L of 0 plus, right? So I go minus 12 plus VL 0 plus 12 volts. So I see that VL of 0 plus is 0. Okay? All right, now what about I sub C of 0 plus? Well, for that, I'm going to do a KCL at this node right here. Okay? So the current coming in there is 0, right? There's 0 current headed this way. And again, I'll focus on my definitions. That has to be equal to, I called this guy here I2. So the current going in is I of 0 minus, that was 0 amps. The current coming out is I2 plus IC of 0 plus. Okay? Now I2, I know because I know the voltage across it is 12 volts and it's 2 ohms plus I sub C of 0 plus, and I solve for I sub C of 0 plus, and that's clearly equal to negative 6 amps. Okay? So that is really how I go through this process. So typically notice I usually have to solve for V sub L of 0 plus by doing a KVL, and I usually have to solve for I sub C of 0 plus using a KCL of some kind. Okay, and I just did that. All right, so let's go now to our step 2. So our step 2 is to basically find the derivatives. So in this case, the one I really need is dVc 0 plus by dt. I'm going to need that ultimately to be able to get my final solution. So to do that, that's pretty easy, right? That has to be equal to I sub C of 0 plus divided by C. This is just the basic relationship that we have for a capacitor. So this isn't too bad because I know I sub C of 0 plus is negative 6 amps. And my capacitor value in this problem is 1/2 a farad. So I divide that by 1/2, and that becomes negative 12. If I want to do units on this guy, I would say amps. No, I would say volts per second. Right? I know that has to be the units because it's d voltage by dt, so it's volts per second. Okay, so that tells me the rate of change of the capacitor voltage initially. So I'm going to need that guy too. So I'm going to write up here dVc 0 plus by dt equals negative 12 volts per second. Okay. All right. So let's keep going. Then I'm asked step 3, find the steady state values of I, L, and Vc. Okay, find the steady state values. So to do that, I basically have to assume, well, long after this switch is closed and the circuits reach steady state, so in other words, long after the inductor currents stop changing and long after the voltage on the capacitor has stopped changing, I need to figure out what the circuit looks like. So long after the capacitor voltage has stopped changing, it's an open. Long after the inductor current stopped changing, it's a short. So I'm going to redraw the circuit. So for step 3, I have 12 volts. I have 4 ohms. The inductor is a short. So then over here I have my 2 ohms. And then the capacitor is an open. So here is the, I guess I'll write it this way, the final, like that. Okay, so that circuit is basically just a simplification of my original circuit where I've replaced the inductor with a short, the capacitor with an open, and this switch is closed now, so this branch is in the circuit. So that tells me I can use the voltage divider relationship to figure out V final. That's going to be 2 over 2 plus 4 times 12, or in this case, it's going to work out to be 4 volts. Okay, so that I'm going to need as well later in the problem. So I'm going to write that up in this box here. So V final is 4 volts. Okay, now we're at the hard part, which is to say we need to write the differential equation. So when we do the differential equation, the thing to remember is I don't make any assumptions now about the capacitor and the inductor. The capacitor and the inductor, the current is changing in the inductor, the voltage is changing on the capacitor, so I need to leave them in the circuit when I do that. All right, so basically I want to redraw this circuit, but just with this branch in place. All right, so step 4, this is the hardest part of the whole thing. Step 4 is this. I've got 4 ohms, got 1 Henry, I've got 2 ohms, and then I've got V of T right there. Okay, and let me leave the definitions I've had all along. This is V4. Okay, this guy is VL. This was written as I. This was written as I2, like that. And this was written as IC. So we're going to stay consistent with those definitions. And this, we recall, is a 12-volt source. Okay? All right, so now we have to go through and we have to solve this guy. All right? Now, just to follow my logic, I'm going to call this, for a second, R1. I'm going to call this guy R2. I'm going to call this guy L. And call this guy C, which is a half a farad. Okay? All right. So to do this, essentially what I'm going to try to do is figure out, all right, I'm going to write a couple of equations here. So I'm going to use my basic tools. So I'm going to say by KCL. Okay, so I'm going to do a KCL at this node right here. Okay, so basically I have I, that's the inductor current, that's going in. That's got to equal the currents coming out. So the currents coming out are I2. and IC. Okay, so what do I know here? I know that I2 is equal to V over R2, right? It's equal to V over R2. And then IC equals C dV dt. Okay, so that's a differential equation, sort of. The problem is, whenever we get our differential equation, we want to have a differential equation that's only in terms of one variable. This guy is in terms of voltage and current. That doesn't work, right? We need to get it just in terms of one of those two. And our desire, given the initial problem, is I want to find the capacitor voltage V of t. So I need a differential equation that's only in terms of V. Okay? So to do that, I have another tool up my sleeve. I can do KVL. So by KVL, I have, let's do KVL around the loop here. All right, so I'm going to do 0 equals -12. So I go from minus to plus on the voltage source. Then I'm going to say I go plus to minus on the 4 ohm resistor. So I say plus V4. Then I go plus to minus on the inductors. That's plus V sub L. And then I go plus to minus on the capacitors. That's plus V. So this guy becomes 12 equals, so V4 I'm going to write as I times R1. All right, so instead of using the 4 ohm resistor value, I'm going to call this guy R1. All right, V sub L is L di by dt. All right, and V is just V. So I see here I've got two equations. This is one of them. This is the other one. Well, what I'm going to try to do is I'm going to try to take this equation and plug it into here. Because if I do plug this equation into here, so I need to plug it into two places. If I plug it in for I, then this term, the first term, IR1, only becomes in terms of V. And if I plug the same equation into the second term, it also becomes only in terms of V. So if I do that, I get 12 equals, so I substitute into this first term, I substitute in V over R2 plus C dV dt. So this right here is my I. So all that times R1 plus L times d by dt of V over R2 plus C dV dt, like that, right? So this again is my I plus V, okay? All right, so I keep going with simplifying that guy. All right, so as I do that, this becomes, let's see, R1 over R2 times V plus R1 C times dV dt plus, all right, what do I get here? So here I get plus L over R2 times dV dt plus, now this term right here, this term, I got a second derivative that comes in. This guy becomes LC times d squared V dt squared, and then I have plus V. Okay? So at this point, I have a second order differential equation. Right? Here's my second order term. And I've got two first order terms that need to be combined together. Okay? And then I've got two zero order terms where there's no derivative. So this guy, if I sort of pull everything together, it becomes LC d squared V dt squared plus, then I got to combine these two terms here. So this becomes R1C plus L over R2 times dV dt plus, I've got this term and this term that need to be combined, so I get R1 plus R2 plus 1 times V, all of that equal to 12. At this point, that guy looks messy, for sure, right? So I want to start plugging in some numbers. So I got to go back. What numbers do I have? So L equals 1 Henry. R1 was the 4 ohm resistor. R2 was the 2 ohm resistor. And C was equal to 1/2 a farad. Okay. So one thing I guess I'll do a little bit before I plug in numbers is, remember our general form of that differential equation. I'll pull up my stuff here. My general form of the differential equation, and I'm going to copy that over here. Okay. My general form of the differential equation is such that I have a coefficient of 1 on the second derivative. I don't have that right now. So I got to divide both sides by LC. So I would have 12 over LC, that's a constant, is equal to d squared V dt squared plus 1 over LC times R1C plus L over R2 all times dV dt plus R1 over R2 plus 1 times 1 over LC times V. Okay, so now I'm going to plug in those numbers there. This guy is basically over here is going to become 24 equals d squared V dt squared plus 5 times dV dt plus 6 times V. All right, that is in the standard form that I have written over here. Okay, so a constant equals a second order differential equation with a coefficient of 1 on that first term. Okay, so at this point I've got my differential equation, so I've done step 4. Now I get to step 5, which is to solve the differential equation. So step 5 is solve. Okay, now the solution V of t is always equal to V final plus V transient. And the transient solution in particular solves the differential equation 0 equals d squared V dt squared plus 5 dV dt plus 6V. We call this guy here the homogeneous equation. Okay, so he solves that. Okay, and we always start out with the guess that this guy's solution is k1 e to the st. We go through that whole process. What we get is our characteristic equation, right? So the characteristic equation says I take the coefficients off of these terms. The first coefficient is 1. So s squared plus 5s plus 6 equals 0. This is our characteristic equation. Characteristic equation. So I need to solve that guy. Now to solve that, I go to the quadratic formula. And the way that I did that in particular is I did that in MATLAB. So I wrote a simple piece of code right here, right? And in MATLAB, there's a simple command called roots that will tell me the roots of this guy. And what I do is I take the coefficients out of this guy. So I write a little vector in brackets. So the coefficient on the highest order term is 1. On the first order term is 5. And on the lowest order term is 6. Put that in a vector and I say, tell me the roots of that vector. And it'll tell me what they are. So I have an S1 and S2 in this case. So let's see, I'm going to take that guy, I'm going to right click that and say evaluate selection. And what's it tell me? All right, so roots 1, 5, 6, my roots are -3 and -2. -3, -2. Okay. All right, so that tells me that this guy, because the roots are real and distinct, this guy is over damped. Okay, he's over damped. So I'm going to go to my notes here. So let's look. So I had different cases. Under damped is where I had complex. Over damped is where I have two real roots that are distinct. So this is my guy. All right. So in this case, I know that V transient is equal to K1 e to the -3t plus K2 e to the -2t. Okay, so I've got two exponentials in my response. And so at this point, I can say V of t is quite simply just V final plus K1 e to the -3t plus K2 e to the -2t. All right, I'm almost done. Now I got to get to my step 6. Step 6 is basically determine the two unknowns in my solution using V sub c of 0 plus and dvc dt of 0 plus. Okay? All right, so to do that, one thing I'm going to do is I'm going to take this little box up here that I created. All right, take that box because I'm going to need that. All right, so step 6 is find unknowns. Now I'm going to copy in here the information I wanted. So V of t is V final. So V final was 4 volts plus K1 e to the -3t plus K2 e to the -2t. Now, in this particular case, taking the derivative is not hard, but I actually did that already in the notes, so I'm just going to jump to that. All right, so in the notes I said, well, so if I had x of t equal to this guy, to take the derivative is very simple. And then I already showed you, here's what happens when I evaluate it. So in this case, I'm going to say V of 0. I just plug in 0 to this equation. I get 4 plus K1 plus K2. And I know that V of 0 is 12 volts. All right, so that tells me that this guy is an equation where I have K1 plus K2 equals 8. All right, now dV dt of 0, right? I could take the derivative of this expression and evaluate at 0. All right, I've already done that over here in the notes. So that guy is equal to K1 times the first root, so K1 times -3 plus K2 times -2, and that's equal to whatever the initial value of the derivative is, which is apparently -12. Okay, so my two equations appear to be K1 plus K2 equal to 8, and -3K1 minus 2K2 equal to -12. Okay, so in matrix form, this guy becomes 1, 1, -3, -2 times K1, K2 equal to 8, -12, like that. So I went and put that into MATLAB. All right, so here's me putting it into MATLAB. So I said 12 minus 4, 8. Okay, so B right here So this guy is B. This guy is A. Okay. So my B vector has 8 semicolon negative 12, right? So these guys are on top of each other. And then over here, my A vector I have, or A matrix, 1 and 1. And then I have a semicolon, then negative 3, negative 2. Remember, the semicolon creates new rows. So this guy here I can think of as AX equals B. So if I want X, I do A inverse times B. So that's what I did here, inverse A times B. Take that, evaluate it, and my answer is negative 4 and 12. So that tells me that K1 equals negative 4 and K2 equals 12. So that tells me that this is 4 minus 4e to the negative 3t plus 12e to the minus 2t. Okay? That now is my final answer. All right, now to validate that, I went and I created for myself a circuit model. All right, and let's look at the original circuit. All right, so here's the original circuit. If you look carefully at these, you'll see that they're the same. All right, I plotted the inductor current and the capacitor voltage. Okay, and let's open up this oscilloscope here. Where's he at? There he is. All right, let's take a look. All right, here he is. Okay, so in this case, what I did was I didn't really flip the switch at t equal to 0, right? I had to allow. I basically just started up assuming that this switch was just open right here, and so for the first 10 seconds, you can see this guy runs for 10 seconds. For the first 10 seconds, basically, I've just turned on this voltage source, and I'm allowing the capacitor to charge up and the inductor to do its thing. Okay, so for the first 10 seconds, that's happening, assuming that this branch is not there. Okay, so what you see is exactly what we said. The capacitor voltage gets to basically be at 12 volts, and the inductor current gets to be at 0. Okay, and then if I look at what happens, the capacitor voltage discharges and gets to a final value of 4 volts. So it looks like it does exactly what we would have sort of expected it to do. All right, and it has sort of an overdamped look like we would kind of expect, right? So he basically just kind of looks sort of exponential. All right, and building that kind of a simulation is not hard. We're going to get into trying to do that kind of thing later on.